unraveling microscopic origins of complex behavior in carbon and sodium using neural network potentials. Although many of you come from different fields and disciplines, you are probably familiar with main concepts of molecular dynamics. Indeed, molecular dynamics is a very powerful computational method for simulating time evolution of a collection of interacting atoms. Atomic trajectories in this method are obtained by numerically integrating Newton's equations of motions. Here I show a very simple outline of a typical molecular dynamics simulation. After setting initial positions and velocities for each atom, we evaluate forces on each atom exerted on it by its neighbors. And then we propagate atoms using Newton's equations of motions. There are actually two important points that I want to emphasize here. The first point is that in order to obtain a reliable simulation, we need to obtain very realistic forces at each step. So these forces are calculated as a gradient of the so-called potential energy function or potential energy surface. This potential energy surface is a function that describes energetics of atomic interactions. So the second point is that this cycle has to repeat it many, many times in order to obtain enough statistics about our system. So we have to perform the cycle for about 1 billion times. So computational efficiency of evaluating the potential energy surface is another important factor that produces reliable molecular dynamics simulations. Normally, when choosing a computational method for a lengthy molecular dynamics simulation, one faces an efficiency-accuracy trade-off, unfortunately. On one hand, we have ab initio methods that are based in which electrons surrounding atomic nuclei are described based on rigorous principles of quantum mechanics. These ab initio methods, they produce accurate description of potential energy surfaces. However, they are not practical for lengthy simulations because of their computational expense. On the other hand, the second group of method is simple analytical approximations to the potential energy surface. They're computationally efficient. However, the construction of these empirical potentials capable of describing various chemical reactions is a very lengthy and difficult process which does not always result in desired accuracy. Are there any alternatives? Is it possible to combine the accuracy of ab initio description of a potential energy surface with the computational efficiency of empirical potentials? Of course, in other words, you can ask, can we have our cake and eat it too? And it turns out that for some systems it is possible. In our work, we use this neural network representation of potential energy surfaces that allowed us to achieve this goal. This methodology was developed by Jörg Baylor and Michele Paranello several years ago. And I will explain step by step what all this scheme means. So first of all, what is a neural network? What is an artificial neural network? Neural network is a mathematical and computational model inspired by functional aspects of biological structures in the brain that is able to capture and represent complex input-output relationships. So when I say represent complex input-output relationships, you already might guess where I'm going with this. So it's exactly what we want. We want to represent our potential energy surface as a complex function of atomic coordinates. Well, this definition probably is a bit general. Let me give you another definition of a neural network, but probably is a bit more specific, does not encompass all the variety of neural networks developed by computer scientists, but it's enough for our purposes. So neural network can be defined by this relatively simple equation. So what happens in it's a multivariate function that essentially works like this. We take our input variables, sum them up with different weights, and then we take a sigmoid function of the sum. Sigmoid function is a function represented by this graph. And then we combine several sigmoid functions of different shapes and different positions to compute our final result. So what is so interesting and unique about this function? This function actually is a universal approximator. It's been proven that a neural network represented by this equation can approximate any continuous multivariate function to any desired degree of accuracy. So the flexibility of this functional form comes from a really large number of these parameters that that can be optimized to reproduce a desired function. All we need is just to present our neural network with a training set. So, and of course here you recognize this schematic that quite often you see in computer science textbooks. It's essentially a schematic representation of this equation. So now let me describe a general approach how we use neural networks to represent potential energy surfaces. Here I use an example of some hypothetical one-dimensional potential energy surface. So first of all, one can calculate ab initio energies for a number of atomic configurations. These ab initio energies can be represented by these red dots on the graph. Then one can feed a highly flexible analytical function represented by a neural network to reproduce these ab initio energies for given configurations. And finally, one can use this function to perform interpolation and obtain energies and forces for new configurations encountered in course of lengthy molecular dynamic runs. So after neural network is parameterized, we do not have to perform ab initio simulations again. Okay, so here I have an example of neural network fitting for a two-dimensional function. Let me just show you this movie, how a neural network can optimize a two-dimensional function. So how it can represent two-dimensional functions. So here we have a neural network representation of this target function, and this is the fitting error. So in the beginning, when we start with random W parameters of our neural network, the neural network representation is nowhere close to the target function. However, as we train the network, you see that this representation approaches closer and closer to the target function, with the fitting error essentially going to 0. Okay, so it's about representing general function. What about representing potential energy surfaces? Potential energy surfaces possess certain properties. For example, potential energy surface, but energy of a system should be invariant to rotations, translations, and order of atoms in the input, right? So, and also we want to have a neural network with such a property that if it's trained for system containing, let's say, 10 atoms, we should be able to use this neural network for a system containing 1,000 or 1,000,000 atoms. So essentially, the scheme of Bell and Parinello is designed to satisfy these properties. In this scheme, the total energy of the system is split into atomic components, and each atomic energy is calculated by its own neural network. Of course, in order to make energy invariant to atom permutations, these atomic neural network should be identical for atoms of the same types. Another important feature introduced in this method is this symmetry function. We cannot just simply take atomic position, Cartesian coordinates of all atoms, and hope to calculate atomic energies, because of course Cartesian atoms are not Cartesian coordinates are not invariant to rotations and translations. So instead we use the symmetry functions as input for the neural networks, and these symmetry functions are basically different order parameters that describe uniquely atomic environment for each atom in the system. So essentially, this part of this general scheme is a regular neural network, regular feed-forward neural network. Okay, so what are the advantages of using neural network compared to empirical potentials? So first of all, neural network completely obviate the problem of guessing complicated functional form of the potential energy surface. This form is automatically determined by the neural network. The entire training process of the neural network is automated, so months of human effort can be replaced by a short computer simulation. And one of the most important points I'd like to make, that accurate mapping ensures that all properties determined by the potential energy surface are described with accuracy compatible with that of ab initio calculations. So let me present two neural networks that we train to reproduce potential energy surfaces for two elements, for sodium and for carbon. We used PBE density functional. It's an ab initio method, which reproduces accurately energetics of interactions in both sodium and carbon. And we included many thousands of these density functional energies to train our neural network. And the number of different atomic configurations is included in this training set is on an order of million. Of course, we included configurations in the pressure ranges that we wanted to reproduce, and temperature ranges. And most importantly, I want to stress this, that fitting error of an independent test set, neural network fitting error, is on the same order of magnitude as convergence error of ab initio simulation. That's why we expect that neural networks will reproduce our ab initio potential energy surfaces with really high degree of accuracy. So essentially, the results of molecular dynamic simulations based on neural networks will be absolutely the same as results one could obtain from ab initio potential energy surfaces. And in these two papers that we published last year, we actually show that this is indeed the case. Many different properties of these systems are reproduced with ab initio accuracy. So okay, so now I'd like to present a couple of applications that we've done using this novel method. So first, we studied graphite to diamond phase transition. Of course, I don't have to spend lots of time convincing you that this process is of tremendous importance in both industry and fundamental science. However, severe restrictions on the maximum system size and time scale accessible in simulations have limited theoretical studies of the mechanism of this phase transition to collective transformation. In collective transformation, small periodic cell results forces all new chemical bonds in the system to form synchronously, simultaneously. So the transition proceeds as an ultra-fast conversion of the entire simulation box. Of course, such mechanism is possible at shock wave compression, but in real static compression experiment, diamond formation is most likely to proceed through nucleation and growth. So that's why it's not surprising that many aspects of the transition cannot be explained by the mechanism of collective transformation. Today I'm going to focus only on this second point, that it's been observed that the transition pressure for obtaining diamond is considerably higher than the graphite-diamond coexistence pressure. Diamond formation is not observed below 10 gigapascal. And the neural network potential enable us to perform the first atomistic study of homogeneous diamond nucleation from graphite. So before I describe the process of nucleation, I'd like to show you how accurate the neural network simulations can be. If you look at different pathways for collective transformation, for concerted path, I show 3 different pathways with different colors here. You see that the energetics of this transformation is very accurately described by neural network. So lines here represent ab initio, density functional theory simulations, and dots are neural network results. They are indistinguishable. Okay, what about interfaces? Since we study nucleation, it's important for us to describe energetics of interface formation very, very carefully. So you see again, lines are ab initio energies and dots are neural network. We reproduce energetics of interface formation between graphite layers and diamond. And also we can calculate ab initio energies for this very, very tiny diamond nuclei inside graphite matrix. And again, we see the agreement here is not perfect, but it is extremely good. It is very, very good. So now what about our model system? We could calculate ab initio energies for tiny nuclei. However, there is no way one can calculate nucleation in the system comprising 150,000 atoms of carbon arranged in the graphite lattice. So this is like a simulation box of the size of 10 nanometers. So in this simulation box, we see the diamond nucleus by constraining interlayer distances between atoms within some predefined radius. Then we heat the system to let surrounding graphite atoms settle around the constrained region, and then we minimize enthalpy of the system, or actually you can say energy of the system at 0 temperature. And these are the results that we get. So depending on the size of the diamond nucleus that we seed in the system, we have different energetics. So most of our curves follow this classical nucleation theory, where at first, as the nucleus grows, the energy increases, and after some critical size of the nucleus, the energy goes down. This is the region after which formation of diamond is essentially spontaneous in the system. And of course, the height of this barrier and the size of the critical nucleus is a strong function of the pressure applied to the system. So what's going on here? What's happening in the system? In order to understand why pressure, why energy and critical nucleoside depends so much on the pressure, we just have to look at the structure of diamond nuclei. As you can see, diamond nuclei become more and more spherical as pressure increases. So it is basically manifestation that it is really hard for graphite layers to come closer to each other to form this diamond nuclei. So in thermodynamic terms, it's possible to say that by looking at the exact expression for free energy of nucleation, it is possible to see why formation of diamond nuclei is impossible at very low pressure. Simply, it is because of the really large misfit strain energy, which is due to large differences in crystallographic axis of graphite and diamond crystals. So essentially, this kind of, by looking at the nucleation process, we can say why diamonds are not formed below 10 gigapascals. And we can also compare energetics of nucleation versus concerted transformation, and we see that nucleation proceeds from much lower barriers at the experimentally used pressure, and a little bit higher pressure, actually concerted transition becomes more favored. So it tells us that diamond formation at high pressure proceeds without formation of well-defined graphite diamond interface. So these are conclusions. I didn't describe all the conclusions of our recent paper. It's been recently published. You can read about it if you are interested in the last issue of Nature Materials. And I just want to, before going to sodium, I want to show you like a short movie of diamond growth inside graphite matrix. You see that red atoms are in diamond configurations and blue atoms are in their graphite configurations. As the nucleus grows, and eventually the entire crystal collapses to diamond. No. The pressure in this simulation just stays constant. But of course, it's the pressure where diamond is more energetically stable than graphite. Therefore, the diamond growth is essentially spontaneous once you reach the critical nucleus size. Pardon me, I cannot really hear you. No, we didn't study actually any time-dependent phenomena in this work. We're going to do it later. So for now, it's just thermodynamics, no kinetics. Okay, so let me jump to sodium now. Why sodium is interesting? Of course, you constantly hear about diamonds, but sodium turns out to be more interesting element than carbon in some sense. So despite being a very simple metal at ambient condition, one can even say a prototype metal at ambient condition, sodium exhibits very counterintuitive and unexpected behavior at high pressure. First of all, it undergoes a series of solid phase transitions, with the complexity of solid phases increasing with pressure. For example, there is a sodium crystal phase that contains approximately 500 atoms in a primitive cell. It's like the most complicated structure of an element ever observed. However, in our work, we concentrated on another most interesting phenomena in sodium. It's this pressure-induced drop in melting temperature. The experimental observation experiments have shown that this pressure-induced drop in melting temperature spans the region of stability of at least 3 different phases, and the temperature, melting temperature, drops from 1000 Kelvin at 30 gigapascal to approximately room temperature at 120 gigapascal. This behavior is unprecedented. It hasn't been observed in any other material. And therefore, maybe it's a bit surprising that, I mean, this behavior has been observed in other materials, but not on this scale. It's the scale of this anomalous behavior of melting behavior is unprecedented. And it is surprising that the nature of this phenomena is unclear. So we used our neural network to reproduce the phase diagram. So we used very accurate thermodynamic integration method that is much better in reproducing melting behavior and phase boundaries than any other methods used before for this system. And you can see that the neural network captures correctly the regions of stability of each phases, and most importantly, it captures this pressure-induced anomalous melting behavior. I must mention here that the total time that is required to obtain this phase diagram is around 50 nanoseconds. We have to perform our molecular dynamics for 50 nanoseconds for a system containing thousands of atoms. These simulations of this time scale and size are absolutely impossible with direct ab initio methods. So maybe you notice that qualitatively the phase diagram looks very similar to the experimental observation, but quantitatively the temperature and pressure scales are a little bit different. So, but carefully analyzing performance of the neural network, we figure out that this error is due to the density functional itself, not to the errors of the neural network fitting. For example, if you look at the energies obtained in the course of molecular dynamics simulations at different temperature and pressure, you see that neural network energies represented by red dots and ab initio energies represented by black dots are essentially the same. The difference between them is much smaller than the difference in energy fluctuations at this temperature. Another important thing that the phase transitions, the transition pressures are very well reproduced with neural network. So the lines here represent density functional results, and these dashed lines represent neural network potential results. Absolutely the same description. And finally, the melting line obtained from the neural network, black line, and the melting line obtained with some approximate ab initio methods, much less accurate than the methods that we use to obtain the neural network line, are approximately the same. So we checked and rechecked the quality of our neural network potential, and we are very happy with this. So what about the nature of this pressure-induced drop? So there was a paper recently published that attributes this unusual behavior in sodium liquid to structural and electronic changes happening inside the liquid as pressure increases. If we look at this order parameter that basically describes the distance from any given atom to its neighbors, to the first closest neighbor, second, third, and so on, normalized to the distance to the sixth nearest neighbor, we see that actually people who published this paper, they saw that there is a contraction of the second coordination shell happening in the liquid as pressure increases. So they said that they saw two different phase transitions in the liquid. And the second transition is driven by the opening of a pseudo gap. This is this small notch on this electronic density of state of liquid sodium. So in order to check our results, we tried to repeat the published results, and we saw that our results are very, very different. They're dramatically different from what's been observed before. As you can see, there is no contraction of the second shell from which the first structural transition was deduced. If we calculate electronic density of state of liquid sodium, we also see that there is no pseudo gap. So our results are in complete contradiction to the previous observations. So what's going on here? In order to understand physical interactions happening in sodium at more detailed level, we resorted to so-called Khaliullin model. This Khaliullin model is quite popular in the physics community. It actually used to be popular in physics community in 60s because of its simplicity. Nowadays, this model is not used so often, and essentially it has two components in it. So first component is electron gas with some given density neutralized by some positive uniform background, and the second component is just two sodium atoms immersed in this electron gas. We can vary two parameters in this model. First parameter is the distance between the atom, and the second parameter is the density of the electron gas. By calculating ab initio energies for this model, we obtained this Khaliullin pair potential that has the following form. You see that the shape of this potential is very unusual. There are long-range wave behavior of the potential, and it really strongly depends on the pressure of the electrons, on the density of electrons. Essentially, this varying density of electrons allows us to mimic the pressure effect on the system. So we analyzed the form of this potential, and we obtained the following analytical expression that fairly well reproduces interactions in liquid sodium. Actually, it reproduces interactions surprisingly well. You can see that radial distribution functions obtained from this Khaliullin model and from the neural network potential, and also from direct ab initio simulations, are essentially the same. They're absolutely, I cannot maybe say absolutely, mostly indistinguishable from each other. So another important result is that now we try to understand which part of this analytic potential is responsible for anomalous melting. So first, we try to take this part. Okay, actually, maybe I should describe the form of this potential in a bit more detail. So the first part, the first term, is this so-called screen-Coulomb interaction, a purely repulsive wall of the potential, and the second term is this oscillatory potential that induces this long-range waves in the potential. So first of all, we decided let's remove this oscillatory part and study behavior of the system described by pure repulsive term. It turns out that we do not see any anomalous melting for this system. However, on the next step, we decided to include the short-range repulsion wall, which is partially includes this oscillatory term. And it's that when we start seeing the anomalous behavior, here I have three curves. One is obtained from neural networks, another is obtained from this gallium pair potential, full potential, and this form is obtained from the short-range repulsion potential that partially includes the oscillatory term. So it becomes clear that this short-range potential is actually responsible for anomalous melting. We tried to look at this potential. However, for a long time we didn't see anything unusual about it. It was just a function steeply going up. However, after we decided to plot forces exerted on atoms due to this potential and plot them on logarithmic scale, we saw that actually this repulsive wall has a softer region. It goes from a very steep behavior described by this line here to much softer and even softer behavior at shorter ranges. So as pressure pushes atoms towards each other, they start sampling these regions, softer regions of the potentials. And it's known that potentials, softer potentials, they produce lower melting temperatures. And this is actually the reason for anomalous behavior in sodium. Okay, so let me conclude. This part of the talk is that we reconstructed the phase diagram and showed that the pressure-induced drop in melting temperature is not a consequence of structural transition in the liquid, as was previously suggested. And we also demonstrated that the reentrant behavior, or anomalous behavior, results from the screening of interatomic interactions by conduction electrons, which at high pressure induces softening in the short-range repulsion. Okay, so this is all that I want to say about our applications of this neural network method. And the last part of the talk, I'd like to describe our implementation. So several years ago, we started with a serial code that could barely treat 6,100 atoms. And the first version of our neural network code was interfaced with DL-Poly. DL-Poly is a relatively known molecular dynamics package, which has many advanced features like thermodynamic integration and metadynamics. So by interfacing the neural network code with this package, we were able to use all its advanced features. And so the second version of the code, we're able to scale to approximately 100 CPUs. After 2 years of work, we managed to make it scalable to approximately 500, 1,000 CPUs. However, after the region of 1,000 CPUs, we do not scale very well because, but essentially, it's not the problem of our neural network module. It's the problem of the DL-Poly code itself. It simply is not designed to scale to so many CPUs, and we are currently working to increase parallel efficiency, and we're making some progress and hope that eventually we will not be limited by 1,000 CPUs, but can go to many thousands of them. And of course, this parallel execution is based on atomic partitioning of the total energy. So essentially, a CPU is assigned a group of atoms in our system. Currently, a realistic size of the system that we can treat with the neural network code contains approximately 1 million atoms, and we can only treat one component systems with this version of the code. And finally, let me tell you about the timing, how much faster neural network performs versus ab initio, direct ab initio simulation. So here I plot the time required to obtain 1 picosecond of molecular dynamics simulation. As you can see, in the region of several thousands of atoms, neural network is approximately 3 orders of magnitude faster than ab initio simulation. This is quite impressive, considering that the accuracy of the simulation is essentially the same. If we extrapolate ab initio timings to the regions of tens thousand of atoms, we see that neural network code that scales linearly with the system size becomes more and more advantageous compared to ab initio simulations that scale. In this region, they still scale as quadratically or even cubically with the system size. So for a system containing 50,000 atoms, the neural network code is approximately 6-7 orders of magnitude faster than direct ab initio simulation. If, for example, our calculation takes 1 day, ab initio simulation of the same quality would take 100 years. If ours, 1 hour, 100 years. 1 day, 3,000 years. So that's essentially gives you an idea of the computational power of the proposed method. So, and let me conclude this presentation by the following points. Neural network potentials enabled us to perform molecular dynamics simulations of high pressure, high temperature processes in carbon and sodium on previously inaccessible time and length scales. And it's not only about whose simulation is larger and longer, it's also about new insights that we're able to obtain from these simulations. We studied the atomistic mechanism of graphite to diamond phase transition and the electronic structure origin of the anomalous melting behavior of dense sodium. And I'd like to say that neural network potential is this emergent methodology. It combines the accuracy of first principle methods with high computational efficiency of empirical potentials. And I'd like to acknowledge people who were involved in this work. Hagai Eshet, with whom we implemented this parallel neural network code. Thomas Kuhne, now professor in Mainz, who supervised all the simulations performed in this work. Jörg Behle, who helped us a lot with developing the potentials and who provide the original version of the neural network code. And of course, Michele Paranello, who supervised the projects and helped us a lot at the moment of frustrations. And of course, I'd like to acknowledge the support of CSCS and High Performance Computing Group of ETH Zurich for the computational time. Thank you very much for your attention, and I'll be happy to answer your questions.